They came without warning, first in 2017, a long, thin fragment racing through the solar system faster than any comet we'd ever seen. Astronomers named it ʻOumuamua, Hawaiian for a messenger from afar arriving first. 2 years later came to Borisov, a true comet rich in ice and dust discovered by an amateur astronomer from Crimea. Then, in 2024, from the edges of the ATLAS survey in Hawaii, a third visitor appeared. 3IATLAS, and this one, scientists realized, was older than the Sun itself. For the first time in human history, we had evidence of matter forged in a different solar system, billions of years before our own star was born. Each of these discoveries reshaped our idea of home. For centuries, we imagined our solar system as self-contained, a family of planets bound to the Sun, but now we know that our cosmic neighborhood has traffic. Small fragments ejected from other stars cross the Milky Way like drifting messages. And some of them, by chance and timing, find their way to us. 3 visitors in 7 years, after billions of years of silence. Coincidence, or have we simply learned to listen? The answer begins with technology. In 2015, NASA and the University of Hawaii activated the Asteroid Terrestrial Impact Last Alert System, ATLAS, a pair of robotic telescopes that scan the entire visible sky several times each night. Their purpose was planetary defense, to find objects on a collision course with Earth, but in April 2024, one of those instruments noticed a tiny point of light moving slightly faster than the background stars. At first it looked ordinary, then its trajectory refused to close. Its path was a hyperbola, an open curve. That meant it was not bound to the Sun. The object was simply passing through, a stranger from another system on a one-way journey. Astronomers traced its motion backward through time. Every model pointed to the same truth: 3IATLAS was already ancient before our planet existed. Its estimated age, about 7.5 billion years. That's 3 billion years before the Sun formed, 5 before the first rocks solidified on Earth. If we could touch it, we would be touching the Milky Way's childhood. Spectroscopic analysis shows that its surface is coated in dark carbon compounds and ancient ices: carbon monoxide, carbon dioxide, ammonia. These molecules freeze only in the coldest regions of space, far from any star's heat. That tells us 3IATLAS formed in a distant outer disk around a different sun and was flung away by gravity before its system had even finished forming. A world half-built, rejected by its own star, wandering the galaxy for billions of years, and we found it by accident. The mathematics are humbling. For an object only a few kilometers wide to cross the narrow plane of our solar system is astronomically unlikely. Yet it happened 3 times since 2017. That means there are millions more out there, the quiet drift of the galaxy's unwanted children. And if 3 have already found us, what will the 4th bring? Around the world, observatories are preparing for that moment. The Vera Rubin Observatory in Chile, the most powerful sky survey ever built, will scan the entire southern heavens night after night, catching every moving object down to the faintest glimmers. Scientists expect that within its first year of operation, Rubin could detect dozens of interstellar objects passing through our solar system. Some may be small as boulders, others the size of mountains. Each one a fragment of another world, another time. Each one a reminder that our Sun is not unique and our story is not isolated. The universe is a network of exchange. Stars give birth, throw out their children, and those children wander until someone, somewhere, sees them again. Somewhere out there, another traveler is already on its way. The only question is, will we see it before it sees us? The story of the next interstellar visitor won't begin with surprise, it will begin with a plan. The first three were accidents, chance alignments of luck and vigilance. The fourth will be captured by design because for the first time in history, our instruments are ready. Across the world's highest mountains and darkest deserts, new eyes are opening. In Chile, at an altitude of over 2,600 meters, the Vera Rubin Observatory waits for first light. Its 8.4-meter mirror and 3.2 gigapixel camera will survey the entire southern sky every few nights, creating the deepest time-lapse of the universe ever attempted. Every new frame will be compared to the last, billions of stars, thousands of asteroids, and occasionally one tiny light that moves just a little too fast to be long. That's how we'll find 3I, the Fourth Interstellar Visitor. Not by accident, but by algorithm. Modern astronomy now runs on data pipelines, neural networks scanning terabytes of sky images, trained to spot the faintest anomalies, those single pixel movements that might otherwise go unseen. Somewhere in that flood of data, hidden among the motions of comets and satellites, the next messenger is already waiting to be recognized. When ʻOumuamua was discovered, its hyperbolic trajectory was only confirmed 5 days after its detection. By then, it was already on its way out. For Borisov, early detection gave us just a few months to observe it before it faded. 3IATLAS stayed bright enough for less than a season. The new generation of telescopes aims to catch the next one as soon as it enters the solar system, while it's still inbound, giving scientists months, maybe years, to study it in detail. And this time, we won't just watch from afar. Plans are already on the drawing board for interstellar interception missions, spacecraft designed to chase and meet these visitors in deep space. NASA's Interstellar Probe concept and the European Space Agency's Comet Interceptor are both exploring how to intercept fast-moving objects entering the solar system. These missions would wait in orbit, engines ready, until a new target is detected. Once identified, they would launch within days, matching trajectories and flying through the visitor's coma, taking direct samples of its material. If 3I arrives soon, it could become the first object ever visited from another star. Imagine a spacecraft built on Earth meeting a fragment that began its journey before the Sun existed. To prepare for that encounter, astronomers are cataloging what we know so far. ʻOumuamua was dry and rocky, Borisov icy and comet-like, Atlas ancient and fragile. Together, they hint at diversity, proof that every star system creates its own kinds of debris. The next one could be different again, metallic or crystalline, or something we've never seen. The odds of another discovery soon are higher than ever. Simulations published in the Astrophysical Journal suggest that a few interstellar objects pass through our solar system every year. We've simply lacked the instruments to see them. With Rubin and Pan-STARRS operating together, scientists expect detections to rise tenfold by the late 2020s, which means the next visitor may already be visible in archived data, just waiting for someone to notice. The search is a race between time and light. Every night, telescopes across Hawaii, Chile, and the Canary Islands feed their images into central networks. Astronomers look for one simple clue: motion. The stars stay fixed, planets move slowly. But a true interstellar object cuts across the star field like a whisper, fast, straight, indifferent. Once an anomaly is found, scientists test its orbit mathematically. If its eccentricity, the measure of how open its curve is, exceeds 1, it's on a hyperbolic path. That's the fingerprint of an object not bound to the sun. The team then checks its incoming velocity. Anything above about 40 kilometers per second relative to the sun means it came from beyond the solar system. Somewhere, at this very moment, a telescope's algorithm may already have flagged such an object, a single outlier in a sea of data points. We just haven't realized what we're looking at yet. In the next few years, as machine learning sharpens and sky coverage expands, the Fourth Interstellar Visitor will almost certainly be found. It might arrive from the direction of the galactic plane or the dark halo above it carrying dust from ancient stars. Its discovery will be the first moment in which prediction and chance meet, evidence that the universe always rewards patience. Because the cosmos doesn't send messages on demand. It sends them when we're finally ready to see them. The first 3 visitors reminded us that the galaxy is alive, exchanging matter, memory, and motion across its spiral arms. The 4th will prove that those exchanges are constant. It will not be an ending. It will be the beginning of a new science, the study of objects born under other suns. And when that moment comes, when the alert flashes across observatories worldwide, astronomers will look up, not with surprise this time, but with recognition. Because they will know that the galaxy has knocked again, and this time we were listening. If a 4th interstellar object is out there, what will it look like? Will it be another frozen wanderer, shedding ancient ice into sunlight? Or something no one has ever seen, a fragment of a world that once orbited a distant, dying star. Each of the 3 we've met so far has told a different story. ʻOumuamua, the first messenger, was unlike any comet ever observed. It spun irregularly, reflected sunlight with a metallic sheen, and accelerated ever so slightly, as if pushed by invisible gas. Some called it a rock, some a shard of nitrogen ice. Others dared to ask if it could be artificial, but most astronomers agree it was a fragment of a planet broken off by tidal forces and sent drifting between the stars. Borisov, in contrast, looked familiar, a true comet. Its blue-green coma glowed with cyanogen and carbon monoxide, elements common in the cold outer reaches of other star systems. It was proof that other planetary nurseries make comets just as ours does. And then came 3IATLAS, dim, ancient, and unstable. A fossil from before the sun, crumbling almost as soon as it was found. Together they form a trilogy of cosmic variety and hint at the diversity waiting in the dark. Astrophysicists now model thousands of possible compositions for the next interstellar visitor. Some simulations suggest that I see fragments dominate, formed in the cold outskirts of young systems before being flung into interstellar space. Others predict rocky cores, denser remnants of shattered planets. There's even a chance that the next one could carry complex organic molecules, the same building blocks found in the early solar system. If that happens, we won't just be studying an object. We'll be studying the raw ingredients of life from another star. Spectroscopic fingerprints from Borisov already revealed cyanide and carbon chain molecules, hinting that chemical complexity is universal. If Fry contains similar compounds, or even amino acid precursors, it could strengthen a remarkable idea that the chemistry of life is not unique to Earth. To grasp what that means, imagine a grain of matter older than our Sun wandering the Milky Way for billions of years. It passes nebulae, supernova shockwaves, and the silent dark between stars. Then, by chance, it crosses our path, and inside that grain lies the same carbon scaffold that builds our cells. That isn't just science, it's a reunion across cosmic time. Based on simulations by researchers at Harvard, Oxford, and the European Southern Observatory, the Milky Way could contain trillions of these rogue fragments, planetesimals ejected from newborn systems during the chaos of planet formation. Each time a giant planet migrates inward or outward, its gravity acts like a slingshot, tossing smaller bodies into interstellar space. That means interstellar debris isn't rare. We're just beginning to detect it. What feels like a miracle, one object passing through our solar system, may actually be routine. We've just opened our eyes. Computer models show that these visitors likely move through the Milky Way's disk at speeds between 20 and 100 kilometers per second. Most will never come close to the Sun, but some, by random chance, cut straight through the inner solar system, brightening just enough to be noticed before fading forever. The next one might already be inbound, crossing the orbit of Neptune right now, unseen against the glow of the galaxy. The truth is, we could be months away from finding it. Maybe the alert will come tomorrow, or next year, or after another decade. But it will come, and when it does, every telescope on Earth and in orbit will turn to that single, anonymous point of light. Scientists will measure its brightness curve, its spectral lines, its orbital eccentricity. They'll determine its composition and origin. With early detection, the James Webb Space Telescope could even study its infrared signature, telling us the temperature, surface materials, and whether it bends gases. And if we're lucky, the Comet Interceptor mission might be retargeted to intercept it directly, taking the first up-close images of matter from another sun. Imagine seeing that image, the surface of a rock that formed billions of years before Earth existed. It would be like looking at the handwriting of creation itself. The more we learn, the more the line between us and them fades. Because these travelers aren't intruders. They are the same material we are made of, the same carbon, the same water, the same dust. The galaxy doesn't isolate its stories, it shares them. Each interstellar object is a fragment of memory, a piece of the Milky Way's autobiography written in stone and ice. And when the fourth visitor arrives, it won't be a stranger. It will be a reminder that before there was Earth, before there was the Sun, there was already a universe building the elements that would one day become us. Every interstellar object has a birthplace, not a planet or a moon, but a moment. A moment when gravity, chaos, and chance combine to throw a small fragment away from its home star and into the open sea of the galaxy. Each visitor we see passing through our sky was once a citizen of another world. Stars are born in clouds of molecular gas, vast nurseries tens of light years wide. Within them, gravity pulls dust and ice into dense cores. As the cores collapse, disks form around young stars. Inside those disks, grains collide and cling together, growing into planetesimals, the raw building blocks of planets. But not every planet survives its creation. Giant worlds move. Their gravity reshapes everything around them. When a Jupiter-sized planet migrates, it can fling smaller bodies clear of its system. In computer models run at Harvard and Cambridge, each forming star throws out billions of kilometer-wide fragments during its first 100 million years. Most will wander forever, never captured again. That's where interstellar objects begin, not as mysteries, but as leftovers of planetary birth. They carry the fingerprints of their parent stars, ratios of oxygen, carbon, and silicon that act like cosmic DNA. To study one is to read a page from another solar system's history. After ejection, these fragments join a slow galactic drift. The Milky Way's gravity binds them loosely within its spiral arms. They travel through dust lanes, supernova shock waves, and magnetic fields, their surfaces darkening over billions of years. Cosmic rays alter their chemistry, turning once bright ice to black organic crust. Some may spend millions of years crossing regions between stars. At any moment, tens of quadrillions of such objects fill our galaxy, a thin, invisible mist of lost worlds. Statistically, a few will always be passing through the solar system. It's a steady rain, too faint to see until our telescopes became sensitive enough to notice. The galaxy has been sending these messages for billions of years. We're just now reading our mail. Data from ʻOumuamua, Borisov, and ATLAS suggest that most interstellar visitors travel along the galactic plane where stars are densest. Their velocities match the average orbital speed of the Milky Way, about 220 kilometers per second around the galactic center. But some move against the flow, likely kicked out by stellar explosions or binary interactions, ancient gravitational battles still echoing through space. When one of these fragments finally approaches our sun, its long sleep ends. Solar radiation melts its surface ice, releasing gas and dust. The object brightens, trailing a tale of memory, a visible record of where it has been. In that moment, it stops being anonymous and becomes part of our story. Astronomers can then measure its composition and velocity, reconstructing its past with reverse orbital integration. In some cases, they can trace its origin back to a specific region of the galaxy, perhaps a young cluster or a supernova remnant. That's how we begin to map the cosmic circulation of matter, the way stars exchange material through time. The carbon in our bodies, the oxygen we breathe, the silicon in our circuits, all once drifted as interstellar dust before being pulled into the sun's nebula. The next visitor we find could carry atoms that will someday belong to new stars and worlds again. In that sense, interstellar objects aren't foreign, they're family on a different orbit. The journey of stars is the journey of everything that comes from them. To watch an interstellar visitor pass through our sky is to witness a small part of that endless cycle, matter leaving one home to find another. And perhaps when we see the fourth visitor arrive, we'll realize that the universe has never been empty. It has always been trading stories between its stars. What does an object drifting between the stars really mean? To science, it is data, composition, orbit, age. To humanity, it is something greater, a reminder that the universe is not still. Every interstellar visitor is a sentence in a language the galaxy has been speaking since before the sun existed. When we measure an orbit, we measure time itself, billions of years condensed into one passing arc. One ʻOumuamua told us that planetary systems throw fragments outward. Borisov proved those fragments can carry the same chemistry we know from home. 3IATLAS showed that matter older than our sun still travels through our neighborhood. Together they redefine our solar system not as an island, but as part of a galactic ecosystem, a constant circulation of dust, ice, and mineral between stars. Supernovae enrich the galaxy with heavy elements. Planetary disks recycle that material into new suns and worlds. Interstellar objects are the couriers of that process, tiny messengers of exchange. If planets are the archives of a star's life, these travelers are the pages torn loose and scattered across the galaxy. For astrobiologists, that circulation has deep implications. If complex molecules, amino acids, sugars, or nucleobases can survive the long voyage between stars, then the seeds of life could spread naturally. This idea, panspermia, doesn't claim life began elsewhere, only that the ingredients may travel farther than we once believed. Laboratory experiments show that simple organics can endure cosmic radiation for millions of years if shielded inside rock or ice. The discovery of glycine, formaldehyde, and other prebiotic molecules in comets and molecular clouds supports that resilience. So, when the next interstellar visitor is analyzed, scientists will search not for living cells but for chemistry, evidence that life's alphabet is written across the stars. If we find the same molecular patterns elsewhere, it will mean life's story may rhyme from one solar system to another. But even without biology, the meaning remains profound. These objects connect us to time scales beyond imagination. When 3IATLAS left its home star, our galaxy's spiral arms were in different positions. The sun did not yet exist, there were no planets, no oceans, no observers. And yet, billions of years later, one of its fragments drifted into our field of vision, carrying with it the signature of those lost epochs. It's as if the universe itself preserved a fossil, not of bones, but of beginnings. To look at an interstellar object is to look at our own ancestry written in dust. Astronomers often call these fragments time capsules. They help calibrate our models of how the Milky Way recycles matter. By studying their isotopic ratios, hydrogen to deuterium, carbon-12 to carbon-13, scientists can trace which generations of stars forged them. Each ratio is a fingerprint of stellar evolution. Through them we see that everything, every atom and every person, has traveled through countless suns before finding form here. The fourth visitor will be one more link in that chain, another proof that creation never stops, it simply moves. Perhaps that is the message the galaxy keeps sending, that we are not apart from it, but expressions of its ongoing experiment. When the next object arrives, the headlines will speak of data and discovery. But behind the numbers will lie a deeper realization that the universe is not a museum of distant stars. It is a living system, still exchanging material, still writing new stories. The fourth interstellar visitor will not just answer a scientific question. It will remind us that the universe never repeats itself, but it always rhymes. One day soon, the alert will come. A faint moving light in a sky of still stars. Astronomers will check the data twice, then 3 times. The curve will not close, its velocity will exceed escape speed. Its origin will lie beyond the sun, the fourth interstellar visitor, for I will have arrived. Within minutes, observatories across Earth will turn their mirrors toward that point of light. Atlas will refine its orbit. Pan-stars will measure its brightness. The Vera Rubin Observatory will plot its motion frame by frame. Somewhere in Maryland or Geneva, a data analyst will see the confirmation line, eccentricity greater than 1. Another messenger from the stars, scientists will name it for I, followed by the initials of the instrument that found it. Its numbers will appear in minor planet circulars, its trajectory uploaded to public databases. And once again, the world will look up, not because it threatens us, but because it connects us. We will have proof that the galaxy is not silent, it is alive with motion and memory. As the days pass, telescopes will gather spectra. Lines of hydrogen, carbon monoxide, cyanide, familiar chemical signatures. Researchers will model its light curve to estimate rotation, composition, and shape. The James Webb Space Telescope will catch its infrared glow, measuring temperature and dust density. A network of citizen astronomers will record its faint trail, echoing across continents in real time. Every new observation will feed into a larger truth that interstellar objects are no longer anomalies. They are part of a constant exchange, the galaxy's way of blending its worlds. The sky, once thought empty, will reveal itself as a river of shared origins. If 4i comes close enough, robotic interceptors may launch. The European Space Agency's Comet Interceptor, scheduled for the late 2020s, is designed for such a moment, waiting in orbit, engines idle until an unpredicted object appears. With quick coordination, it could swing into a new trajectory, racing outward to meet the traveler head-on. Cameras would capture its shape. Spectrometers would taste its dust. For the first time, humanity would hold direct data from another solar system. Perhaps it will look ordinary, a frozen stone, black and silent. Or perhaps it will glint with minerals unseen in our neighborhood. Either way, its existence will whisper a simple fact, that the universe is one continuous experiment, scattering pieces of itself for others to find. The fourth visitor will not bring answers, it will bring perspective. When we think of deep time, we often imagine stillness, but the Milky Way is never still. Stars orbit, collide, dissolve, their fragments drift. Our sun, too, will one day cast its own remnants into the void, future travelers that may one day pass another civilization's sky. To them, we will be the mysterious visitors, and perhaps, across that unimaginable distance, another voice will ask the same question we ask now. What comes after this one? In the meantime, astronomers continue their patient watch. Every night, thousands of telescopes scan the sky, logging data into global archives. Machine learning models sift through the noise, searching for the next anomaly. It may take months, it may take a decade, but somewhere out there an ancient fragment is moving toward us. It carries no message, yet it says everything. When it arrives, we'll track it, measure it, name it, but after the science is done, something quieter will remain. The realization that discovery is not about endings. It's about noticing what was always there. The universe is older than our sun and younger than our curiosity. And somewhere in that span between time and wonder drifts a small object that has been traveling for billions of years, heading home for a brief moment through our sky. Perhaps the fourth interstellar visitor isn't coming to us. Perhaps we're the ones finally learning to see it.